Hello, welcome to this new video. In this video we are going to discuss an important result in graph theory, and this result is very famous as the quadratic reciprocity law. What the result says, the result states that if P and Q are two distinct odd prime numbers, if P and Q are two distinct odd prime numbers, then the Legendre symbol P bar Q, the Legendre symbol P bar Q into the Legendre symbol Q bar P equal to minus 1 to the power of P minus 1 into Q minus 1 divided by 4. The Legendre symbols, product of the Legendre symbols P bar Q into Q bar P equals minus 1 to the power of P or minus 1 raised to P minus 1 into Q minus 1 divided by 4. It can also be written P minus 1 by 2 into Q minus 1 by 2. The power of minus 1 can be written, it can be split and written. And to prove this, we can begin with the Gausslemma. We use the Gausslemma. Using Gausslemma, and also we use the theorem 9.7. Theorem 9.7 of the text Analytic number theory by Apostle. We use the theorem 9.7 of the text Analytic number theory. Introduction to Analytic number theory, the text Introduction to Analytic number theory by T.M. Apostle. We can now write that using the two. We can write that the Legendre symbol P bar Q equal to minus 1 to the power of m, minus 1 to the power of m, or minus 1 power raised to m. What is m here? M is the number of you can recall that m is the number of residues greater than q divided by 2. See, this is the number. Then see the lower number, and the number used here after the bar should be considered here for dividing it by 2. So the number, the residues, we count the number of residues. We count the residues. The number of residues is counted whose value is greater than q by 2. That is the second prime number in this expression. Okay, and when the number q by 2. But when do we count? How do we count that? When the number is p, 2p, or 1 into p, 2 into p, 3 into p, etc. to q minus 1 divided by 2p. When these when the numbers in this list are all divided by q, you get remainders, and the values of the remainders whose values are less than or equal to q minus 1. See, the remainders are strictly having values greater than 0 and less than q. Among these out of these values, these remainders, some of them are strictly will be greater than q by 2, some of the remainder valuus. So you have to count the number of those values. Since p is an odd number, an odd number, an odd prime number, see, we have that, since p is an odd prime number, that using the second part of that using the second part of the result, 9.7, considering the result 9.7, this is you can see that there exists a second part. That result has a second part. Using the second part of the result, since the number q is since this number since the number p is an odd number, odd number, this number is an odd number, since p is an odd number, and we have that m is then congruent to sigma summation from t equal to 1 to q minus 1 divided by 2 of the expression summation taken between the limits 1 and q minus 1 by 2. So this depends on that second number taken, this q. So this limit is decided, and but the expression taken here is the greatest integer, which is contained in the number t into p divided by tp by q, in the quantity tp by q, where t varies from 1 to q minus 1 by 2. So t into p divided by q in square bracket you have to take. Then it will be, this quantity will be when we subtract this quantity from m, we can divide that quantity completely by 2. That means m is congruent to this quantity, the sum mod 2. So this will be taken equal to the first expression, number a expression, or the equation a. Similarly you can consider the reverse one, the reverse Legendre symbol q bar p. There also you can apply the all the same steps you can apply. You can follow all the steps that we have considered in the previous case. Exactly the same way we can proceed, because here also we have a prime number, p is a prime number and q is an odd number, and p is also an odd prime number. So you see, all the conditions are satisfied. Therefore the Legendre symbol q bar p is equal to minus 1 raised to n. See, this n may be then different, this power n. What is n? N is the number of in this case n is the number of residues greater than p by 2. See that change, that difference. Here n is the number of residues greater than p by 2 when the numbers in the list q, 2 into q, 1 into q, 2 into q, etc. to p minus 1. See, here we have p minus 1 into q divided by 2. That part is missing here. These numbers are q, 2q, etc. to p minus 1. P minus 1 into q divided by 2 is the number, the last number, when these numbers are divided by p. So and also, since q is an odd number, you get that n is congruent to summation from s equal to 1 to s. This s is a variable. Here s can take values from 1 up to p minus 1 by 2. Then summation of s equal to 1 to p minus 1 divided by 2 of s into q of s into q by p in square bracket, taken in square bracket, modulo mod 2. And this is the expression b, named b. So when we write, since we have this expression, and considering the two expressions, you see that is the Legendre symbol q bar p equal to minus 1 raised to n, and p bar q equal to minus 1 raised to m, then you can multiply them, p bar q into q bar p. Therefore p bar q into q bar p will be equal to minus 1 raised to m into minus 1 raised to n, and that can be combined to get minus 1 raised to m plus n. So m plus n is the power of minus 1. Next we proceed, and we can then complete, by proceeding this way, you can complete the proof by showing that summation sigma t equal to 1 to q minus 1 by 2 of tp by q in square bracket plus summation s equal to 1 to p minus 1 by 2 of sq by p equal to p minus 1 by 2 into q minus 1 by 2. If you can show that this quantity is equal, actually it is not equal to, and you can show that this is congruent to p minus 1 by 2 into q minus 1, p minus 1 by 2 into q minus 1 into mod 2. If we can show that this quantity is congruent to Okay, and that correction should be made, and exactly we cannot show that this quantity is equal to this quantity. But you can show that this sum, the sum here we have two sum of two sums. The sigma, the first sigma plus the second sigma, you can show that it is congruent to p minus 1 by 2 into q minus 1 by 2 mod 2. That means by adding some even number to this quantity, you get that either to the left side or to the right side, you can add some 2 into k, some quantity 2 into k. That's a multiple or the double of some integer quantity 2 into k, where k is some integer. So that can be an even number. By adding an even number, by adding an even number either to the left side or to the right side, you can make this equation. So this equation is not complete now. It can be made complete by it can be replaced that actually it is congruence then mod 2, but that can be made that congruence can be replaced by equal symbol. This symbol can be given, but either by adding some quantity 2 into k to the left side or to the right side, not to both sides. One of the sides you can add that quantity. Okay, then see, this is we are stating this as a claim, and this is the claim now that we make this claim. Okay, and now we are going to prove this claim. Which claim? And this is the claim that we made. But no, this is, here we have congruence. This one more line is there, and then mod 2 is the term missing here. It is congruence and then mod 2. After this expression we have mod 2. We are going to prove that claim. So for proving that claim, we define a function. New function we are going to define. We define a function. That function is f of xy. That is given the name f of xy, fxy. That means it takes two variables, x and y. See, x and y, these variables are newly introduced. These are two new variables. It has no connection with any part of in the previous discussion here in this proof. See, we are taking, that means the variables x and y are freely taken, are independently taken, and we define a function f of xy. But there you can see that on the right side p and q are used, but that has connection because these p and q are the numbers, are the odd numbers that we have specified in the statement of the result. These are the odd prime numbers. P and q are the odd prime numbers that we have already taken. So these are the quantities, fixed quantity. P and q are the fixed quantities, but x and y are variables. But these variables can vary only subject to the given condition. Here these must be integers. X and y must be integers, and these integers must belong to this range. Or natural numbers belong to the range. X is a natural number where 1 less than or x is there, 1 less than or x less than p minus 1 by 2, and y is a natural number which satisfies the condition 1 less than or equal to x, y less than or equal to q minus 1 by 2. And these are the range of variations of x and y. But these x and y are integers, positive integers, but they act as variables. We are now going to make some claims on this function or we are going to prove some properties of this function, newly defined function f of xy. First of all, we claim that, or we say that fxy is non-zero. Fxy, the function, what are the function values? We define a function f of xy, then the function which is defined as q into x minus p into y. This is the definition, qx minus py. So the function values, of course the function values are obtained by calculating qx minus the quantity, qx minus py can give you the function value. And these function, about these function values, it is here stated that is these function values can never be equal to 0. Fxy is not equal to 0. So to prove this, to argue this, finally you want to prove, but if you want to argue this family, then you have to show that this function, or the function value is not equal to 0. Always it is not equal to 0. So for that, let's for the time being, let us assume that f of xy equal to 0. Suppose f of xy equal to 0, but f of xy equal to 0 if and only if that if and only if x equal to p and y equal to q. Or we have the two situations. So assuming that f of xy equal to 0, you can, if you take this as equal to 0, then one situation is that in which you get 0 is that here you can take p, q into p, and here you can take y equal to q. You can assume that x equal to p and y equal to q, then you get 0. But that situation is not possible, because according to the given range of variation of x, since x and y can vary only in using this condition or within this range, then x cannot be equal to p and y cannot be equal to q. So that possibility is thus removed. That is not possible. That case is not possible. So what is the remaining case? The remaining case, we have to think about the remaining case. Okay, and okay, then okay, then we once again, if you think that this happens, suppose this happens. Okay, otherwise then also if you take that this is equal to 0, then you can say that x by y equal to, see, you can write then x divided by y by rearranging this quantity. Well, we are going to check whether any other situation exists. So the one of the situation that is most possible, the most probable situation that we have discussed, and we have eliminated that situation. We have verified that situation does not happen. But you want to verify whether any other situation exists in which for that value of x and y we get 0 for the function fxy. Yes, you just assume that it is equal to 0. Then you can write qx equal to py, right? By transferring minus py to the right side, you can then write qx equal to py, and you can then make the ratio. See, x by y, then what is then x by y? X by y will be then equal to p by q, right? Then x by y equal to p by q. So you can say that the ratio x by y, that is the lowest value, or in the basic form, you can say that the ratio x by y, x divided by y, is in the basic form, because p and q are prime numbers, right? Since p and q are prime numbers, therefore x divided by y equal to p divided by q, that ratio is in the simplest form. A similar other quantities. It is clear that other quantities for x and y, other values of x and y, or other values of x and y, that can give us 0 from that equation as the value of the equation, as the value of the function. So that can generate 0 as the value of this function. Can be only the multiples of, or other values can be only the multiples of then p and q, or constant multiples, only some integer multiples of p and q. So from that it is clear that it's x divided by, since x by y equal to p by q, so you can then take other values as some k into p and k into q. See, k into p and k into q, where k is equal to 1, 2, 3. Yeah, in the case k equal to 1, the case k equal to 1, that is the lowest case, the least value of k. That case we have verified, and in that case we have seen that it is not possible. That situation is not possible. All the remaining values are can be given by taking k equal to 2, 3, etc. Those values 2, 3, etc. But when k equal to 2, then you are going to get x equal to 2p and y equal to 2q. See, even in that situation, you know, x, the value of x is far above this upper limit. When it is 2p, when x is equal to, if you are going to take x equal to 2p, then it is far above the upper limit. So similarly, when y equal to 2q, that also is very larger than this limit. So it falls above this upper limit, upper value. So it is now clear that there is none of the in none of these situations you know, you are going to get a 0 here, because all the values, all the possible values of x and y that can create 0, that can generate 0 for this function f, and that all those values strictly belongs to the complement of this this limit. You know, that all those values fall far away from the upper value here for x and y, for both x and y. Therefore, all the possibilities that the function is equal to 0 is now removed. So it is clear that the function, you can restate that situation in such a way that this function value, always the function value obtained is positive or negative. It can never be equal to 0. So the function value is either positive or negative, and also it's an integer value. Why? It's because we are considering only the integer values in the range 1 to p minus 1 by 2 for x, and in the range from 1 to q minus 1 by 2 for y. Since we are considering only integer values, you know, you are going, because and also you know that p and q are integer values, so you are going to get only the integer values for the function f. Okay, that is another important thing about the function values. So we have seen this. We have seen two important facts about the function value. It can never be equal to 0, and all the values are integer values. It can either be negative or it can be positive. Okay. Next, we make the claim that another claim. What is it's coming? Another claim is coming for two different points x and y. We are going to make another fact about the. We are going to establish another fact about the function values for two distinct points x y and x prime y prime, or x dash y dash. We are considering two distinct values of x y values of the coordinates, the paired values x y. We are considering two different points of the paired values. We get that two different points, you know that at least either x is not equal to x prime or y is not equal to y prime. So we consider two different values x y and x prime y prime. Then corresponding to these two different values, we can say that fxy, the corresponding we can find the corresponding function values also. So those corresponding function values will also be different. So if we take two different points xy and x prime y prime, we get always we get two different values for the functions f of xy and f of x prime y prime. Yeah, we can prove this. We are going to prove this because how can we prove that? We subtract one value from the other, considering that function value f of xy minus f of x prime y prime, and you know that is equal to, using that value f of xy is equal to qx minus py, then minus f of x prime y prime is qx prime qx prime py prime, equal to, then rearranging that we get that q into this quantity is equal to q into x minus x prime and p into y minus y prime. We get that q into x minus x prime and p into y minus y prime, and that then becomes it becomes in the form of and this takes the form of another function value at the point x minus x prime and y minus y prime. So we get that so we can write that it is equal to f of x minus x prime y minus y prime. That is the function value at the point x minus x prime y minus y prime, and clearly it is not equal to 0. It's not equal to 0. It's because we have proved that none of the function value equal to 0, so it is not equal to 0 since all f values are non-zero, and we get that. So it is clear that then for clear that there are p minus 1. See, since all function values are now different, it is clear that all function values are different. Then none of the values are equal to 0. All function values corresponding to the pair x comma y, all the we have a function value, and all these values are different. Thus it is clear that there are total how many function values are there, since x can have values from 1 up to p minus 1 by 2, and y can take values from 1 up to q minus 1 by 2. The total number of function values equal to p minus 1 by 2 into q minus 1 by 2. Since we can obtain the pairs x comma y how many different ways, p minus 1 by 2 into q minus 1 by 2 different ways. So the total number of function values equal to is given. Total number of different function values is given by this quantity p minus 1 by 2 and q minus 1 by 2. Next we are now going to count the number of f values which are positive. We are going to count the number. We know that the function values are either positive or negative. We are trying to count the number of function values which are strictly positive, and then after that we will count the number of function values which are negative. So in two different steps we will do that. First we try to count the number of positive function values. See, for that we take f of xy, a function value we consider f of xy, that's equal to qx minus py, and we assume that this is positive. So we take that the value is greater than 0, it's positive, and then we get that qx is greater than py, and this implies that by dividing both sides by p, we get that qx by p is greater than y. So whenever we assume that f of xy is greater than 0, it's positive, and we get that by rearrangement we get that y is less than qx divided by p. Therefore y is less than the quantity qx divided by p. And here this is done by fixing x. Here we fix x. For this step we fix the value of x. That means we consider a particular value of x where x equal to 1. First we consider, then after that, after obtaining this quantity, then we go to x equal to 2, we calculate this quantity, and again for x equal to 3 we calculate the quantity. So by considering x only, we take this positive, we try to count the positive function values, the number of positive function values by with respect to x we count. So we have to consider how many cases x equal to 1, x equal to 2, and that way we have to consider up to the upper limit of x, that is p minus 1. What is the upper limit of x? X is p minus 1 by 2 is the upper limit of x. So all those x values you have to consider one by one, and in each case you can count the number of function values, positive function values. Thus this quantity can be rewritten as y is less than qx by p in square bracket. That means the highest integer which is less than the quantity qa which is contained, highest integer value, highest positive integer value contained in the quantity qx divided by p. That means we are removing that the decimal portion from the number qx divided by p, and that many y values can give us, if you fix an x, after fixing an x, if you check this condition, if you apply this condition, you can see that for those y values which satisfy the condition, wherever for whatever values of y which satisfy the condition that y less than the here here we have less than or equal to, actually. Yeah, it's a mistake. Here you have to consider, because this is greater than y, this quantity is greater than y, qx is greater than y, but here you have to consider y less than or equal to, actually, and there is a mistake, less than or equal to qx divided by p in square bracket. So for a fixed value of x, if y is yeah, there's also it's a mistake repeated. Y is less than or equal to qx by p, then we get that y f of xy is greater than 0. Then we get f of xy greater than 0. So it means that for a given value of x, whenever y is less than or equal to, so I may correct it once again, y is less than or equal to, here you have equal to, y is less than or equal, sorry, here we have less than only, and since we don't take the square bracket, so y is less than qx by p, then we get that means y is less than or equal to qx by p in square bracket. And so by varying, by varying x from 1 up to p minus 1 by 2, by varying the quantity 1 up to p minus 1 by 2, okay, by varying the quantity up to p minus 1, yeah, that's correct, up to p minus 1 by 2, then we get all positive f values. We get the total number of positive f values. So number of positive f values is equal to summation from x equal to 1 to p minus 1 by 2. This says that we are counting the number of positive values corresponding to each value of x of the quantity qx divided by p. Okay, and similarly we can count the number of negative values, but here we fix the y value. First we here in this case we fix y, or we are going to count the number of negative function values by considering y, or with respect to y. So next we count the number of negative values of f with respect to y, and first we fix a particular y value. See, a particular y value is fixed, and that y belongs to the range 1 less than or equal to y less than or equal to q minus 1 divided by 2. Then f of xy is taken, and that equal to qx minus py is it is then negative, it is then less than 0. So we get we can write that qx is less than, we get that qx less than py, and that implies x is less than py divided by q. So those values, say here it is correct, it is correctly written. Since x is less than py by q, we consider that those values correspond for those values of x, for all those values of x which belong to which satisfy the condition x less than py by q, all those values, it strictly satisfies the condition x less than or equal to py by q in square bracket. Less than or equal to is correct. This is correct. This way, in that case also, in the previous case also, you have to put that equal to there, greater than or equal to symbol must be there. So total number of negative values are obtained by considering, by varying y from 1 up to q minus 1 by 2, means you have to consider all y values. The corresponding number of x's will be then taken. Therefore, total number of negative y values equal to summation from y equal to 1 to q minus 1 divided by 2 of py by q in square bracket. See this quantity py divided by q in square bracket. Therefore total, that the total number of function values equal to the total number of positive values function values plus total number of negative function values. And also we know that in an independent way we have seen that the total number of function values equal to p minus 1 divided by 2 into q minus 1 divided by 2. See here also in another way we can also write that another way we can write that this quantity is equal to that quantity is equal to the sum of the quantities equal to summation from x equal to 1 to p minus 1 by 2 plus summation from y equal to 1 to q minus 1 by 2, by adding the two quantities. Since we calculate the quantities separately, independently separately we have calculated the negative function values and positive function values. So adding the values, negative and positive values, then we get that the total number of function values equal to summation sigma qx by p in square bracket plus sigma py by q in square bracket, and that quantity equal to p minus 1 divided by 2 into q minus 1 by 2. And this is the claim, this is the proof of the claim. Okay, next okay, therefore this quantity is equal to this sum equal to this quantity. Okay, next we know we refer that expression A. Using A, we using the expression A, we can expression A is in this proof itself, we have in the beginning the expression A, we have to refer that. See, this is expression A. The expression A, since we have there m is congruent to summation from t equal to 1 to q minus 1 by 2 into tp by q mod 2, you know that. Okay, therefore you can now write that you can add a multiple of a doubled quantity of some integer, or you can add here 2 into k1. 2 into k1 where k1 is some integer, add, and then you can make this congruence. You can replace this congruence by equality symbol. You can replace. Okay, then you can write m is equal to. Okay, then m is equal to this quantity plus k 2 into k1, because here we take modulo. This expression is written with respect to modulo 2. And similarly, you can refer the statement B. There also you can do the same thing, and thus we can rewrite that these two expressions. Okay, then thus by modifying A, you can write that m is equal to the same is done here. M is equal to summation tp by q in square bracket plus 2 into k1, and n is equal to sigma sq by p in square bracket plus 2 into k2, where k1 and k2 are two suitable integers. Then by adding m and n, m plus n equal to sigma first second summation plus second summation plus 2 into k1 plus k2, and therefore minus 1 raised to m into minus 1 raised to n. This is into multiplication. Minus 1 raised to m into minus 1 raised to n equal to minus 1 raised to m plus n equal to minus 1 raised to summation of minus 1 raised to summation sigma tp by q plus sigma sq by tp by q plus sigma sq by p. SQ by P. See here this quantity plus actually this 2 into k1 plus k2 is there. 2 into k1 plus k2 is there, but you know that when we expand that that expression, then minus 1 raised to an even number you will get. You have to you will get here this quantity will be multiplied by minus 1 raised to an even number, minus 1 the power of an even number, so that quantity will be plus 1, and hence it has no effect. Therefore you get that this is equal to minus 1 raised to m plus n is equal to minus 1 raised to summation first sum plus second sum equal to that since this quantity is obtained, therefore this that can be replaced by, because we have proved that in the first part in above we have just above we have proved that this quantity is equal to p minus 1 by 2 into q minus 1 by 2. So you can replace that quantity and hence get that the minus 1 hence you can obtain that this quantity minus 1 raised to m plus 1 is equal to minus 1 raised to p minus 1 by 2 into q minus 1 by 2. Okay, and therefore this is the let's go to the to verify whether we have reached the end of the proof. We have to go to that is p minus 1 by p minus p bar q into q bar p. Thus we have obtained that p bar q into q bar p it's equal to p bar q equal to since p bar q into q bar p, we have proved that it's equal to minus 1 raised to m plus n. We have shown here that p bar q into q bar p, since p bar q into q bar p equal to minus 1 raised to m plus 1, somewhere we have proved that. here we have written the, here we have written, since you see this expression, my p bar q into q bar p is equal to minus 1 raised to m into minus 1 raised to n is equal to minus 1 raised to m plus 1. So since m minus 1 raised to m plus n, we have obtained now, here we have obtained that minus 1 raised to m plus n is equal to minus 1 raised to p by p minus 1 by 2 into q minus 1 by 2, and so we can, thus we have completed the steps of the proof. So this is the end of that proof. Thank you.